Hi friends, today we something about instantaneous centers. Previous classes we discussed about instantaneous centers. Today we discuss something about the location of instantaneous centers. So Arnold Kennedy or three center in line theorem. This is one of the principles we are utilizing for instantaneous centers. Arnold Kennedy's theorem states if three bodies move relative to each other, they have three instantaneous centers and on a straight line. The method of locating the instantaneous center in a mechanism: first of all, determine the number of instantaneous centers n by using the relation. Make a list of all the instantaneous centers in a mechanism. Since for a 4-bar mechanism, there are 6 instantaneous centers. Therefore, these centers are listed as shown in the following table, as known as bookkeeping table. So here instantaneous centers 12, 23, 34, 13, 24, then 14. Locate the fixed and permanent instantaneous center by inspection, from which the diagram L12 and L14 are fixed instantaneous centers, and L23 and L34 are permanent instantaneous centers, from which the diagram what we seen here. So this is the 4-bar mechanism. It specifies a circle diagram. So locate the remaining the neither fixed nor permanent instantaneous centers or secondary centers by Kennedy theorem. This is done by the circle diagram as shown. Mark points on a circle equal to the number of links in a mechanism. In this present case, mark 1, 2, 3, 4 on the circle. Join the points by solid lines to show that these centers are already found. In the circle diagram, these lines are 1, 2, 2, 3, 3, 4 and 1, 4 to indicate the centers L12, L23, L34, L14. In order to find the other two instantaneous centers, join two such points that line joining them forms two adjacent triangles in the circle diagram. The line which is responsible for completing two triangles should be a common side to the two triangles. Join 1 and 3 to form a triangle 1, 2, 3 and 3, 4, 1, and instantaneous centers L13 will lie on the intersection of L12, L23 and L14, L34 produced if necessary on the mechanism. The instantaneous centers L13 is located join 1 and 3 by a dotted lines on a circle diagram and mark numbers 5 on it. Similarly, the instantaneous centers L24 will lie on the intersection of L12, L14 and L23, 3, 4 produced if necessary on the mechanism. Thus L24 is located join 2 and 4 by dotted lines on the circle diagram and mark 6 on it. Hence all the 6 instantaneous centers are located. So problem number 1. So in a pin joint 4-bar mechanism as shown in diagram, AB is equal to 300 mm, BC is equal to CD is equal to 360 mm and AD is equal to 600 mm. The angle BAD 60 degree. The crank AB rotates uniformly at 100 rpm. Locate all the instantaneous centers and find the angular velocity of the link BC. The diagram shown here. So this is the problem number 2 we will discuss in the upcoming sessions. Locate all the instantaneous centers of the slider crank mechanism as shown. The length of crank OB and the connecting rod AB are 100 mm and 400 mm respectively. If the crank rotates clockwise with the angular velocity of 10 radian per second, find velocity of slider A, angular velocity of connecting rod AB. So So relative velocity method, the motion of a link, velocity of any point in a link with respect to another point on the same link is always perpendicular to the line joining these points. On the configuration or space we can specify. Let omega is equal to angular velocity of the link AB about A. We know that velocity of point B with respect to A, so that is VB, A is equal to AB bar, that is equal to omega AB. Similarly, the velocity of any point C on AB with respect to A. So VCA is equal to AC is equal to omega AC. From the equation 1 and 2, VCA by VBA is equal to AC bar divided by AB bar is equal to omega AC divided by omega AB is equal to the omega cancel together. So we can write AC by AB. Rubbing velocity at a pin joint. The links in a mechanism are mostly connected by means of pin joints. The rubbing velocity is defined as the algebraic sum between the angular velocities, the two links which are connected by pin points multiplied by radius of the pin. Consider two links OA, OB connected by the pin joint at O. Omega 1 angular velocity of the link OA or angular velocity of the point A with respect to O. Omega 2 is equal to angular velocity of the link OB or angular velocity of the point B with respect to O, and R is equal to radius of pin. According to the definition, rubbing velocity at the pin point O is equal to omega 1 minus omega 2 into R. If the links move in the same direction, it specifies. If omega 1 plus omega 2 into R, if the links move in the opposite direction. Note that when the pin connects one sliding member and the other turning member, the angular velocity of the sliding member is 0. In such cases, the rubbing velocity at the point is equal to omega into R. Omega is equal to angular velocity of the turning member and R is equal to radius of the pin. So problem relates relative velocity method.